Hello and welcome to Light the Deep. For the entirety of human history, the perception has been divided. You see with your eyes, you listen with your ears, and you reason with language. But inside our mind, these signals do not stay separate. They blend. Basically, an apple is not just a shape. It's not just red in color. It is a crunch. It is also a sweet taste that is associated with it. And for some people, it is also a status symbol. All in all, it is a unified experience. We call this integration in neuroscience, but we call this multimodal revolution in computer science. So we are no longer building digital calculators that can predict the next best word. We are building digital synesthesia. But building a mind that can perceive physical world in the way it does requires to break the fundamental laws of computer architecture. Let's jump in and see what it means. For decades, the data was segregated. On the left, text, the domain of recurrent neural networks. They viewed the world as a thin ribbon of symbols processing one character after the other in a strict sequence. In the center, images, the domain of convolutional neural networks or CNNs. They viewed the world as a grid of pixels, slicing small windows across the screen and to find the edges and the textures. On the right, audio, treated as raw signal processing in physics and normal physics applied on it. These architectures are isolated. They were mathematically incompatible. A CNN could not ingest a sentence and an LSTM could not see a pixel. They spoke different languages, created fragmented landscape of narrow, brittle intelligence. Basically, they were incompatible with each other. They could not talk with each other. They just could not communicate with each other, therefore could not perceive things altogether. Now, to build a unified architecture and to build a generalized intelligence, we had to dissolve these walls. We needed a unification event. The breakthrough wasn't about teaching a text model to see, but it was about realizing that text, pixels, and sound waves are just different shadows of the same reality. We moved to a unified latent space by projecting all these modalities into a high-dimensional vector that is in the same space. We created a shared geometric universe. In this sphere, the math stops caring whether the input was a photon, a sound wave, or a phoneme. It only cares about the semantic meaning. Think of the concept apple. To a computer, apple is traditionally just a string of ASCII characters, A, P, P, L, E, 5 bytes of data. But to you, it triggers a neural cascade. You visualize the red roundness, you simulate the auditory crunch, you recall the waxy texture. This is biological synesthesia, the effortless blending of senses. The goal of modern AI architecture is to replicate this graph artificially. We want the model to act as a central hub where the vector for the word apple and the vector for the image apple collapse into the same coordinate space near each other, related to each other. Now it's time for the visual revolution. But how do we physically force a picture into a model designed for language? We use the vision transformer, commonly known as VIT. The logic here is profound. We take an image, say 224 by 224 pixels, a standard in CNN world. A CNN would scan this pixel by pixel. The transformer does something more aggressive. It slices the image into patches, 16 by 16 usually. Now watch closely. A 16 by 16 patch contains 256 pixels. Each pixel has 3 color channels, red, green and blue. That gives us 768 raw numbers. We take this grid and flatten this into a single 1D vector, a list of 768 numbers. We then pass this through the linear projection layer. The layer mathematically transforms the raw pixel intensity into a concept vector. Suddenly, the patch of image is no longer pixels, it's a visual token, mathematically identical to the word embedding, both in the terms of dimension and in the terms of concept. By adding positional embeddings, it stamps that I say I belong to the top left corner. So we allow the transformer to attend to the entire image at once, and it can compare a patch of dog's ear to a patch of dog's tail instantly, understanding the global structure of the image as if it were a sentence. Now that was great for images. What about the audio? We apply an even more clever transformation to sound. Raw audio is messy. It's a 1D stream of air pressure changes over time. To an AI, the waveforms are noisy and inefficient. So we borrow a trick from physics, the fast Fourier transform. We take the waveform and decompose it. We check how much bass is in this millisecond, how much treble. We track the frequency snapshots into next to each other and create the MEL spectrogram, the thing that you see when you record in your iPhone or in your Android phone, right? Look at the result. It has an x-axis representing time, a y-axis representing frequency. The intensity is color. Do you see what happened? We turned audio into image. Specifically, we use the MEL scale, which warps the frequency axis to match human hearing, giving it more detail to the voice and sounds we actually care about, and compress the high frequency static. Once audio becomes an image, we can feed it to the same exact pipeline used for vision transformer, slice it, patch it, flatten it. The model doesn't hear the sound, it reads the visual signature of the harmonics. Now when we train the model on petabytes of these multimodal data, how do these different senses align? They don't just magically land on the same spot. We use a technique called contrastive learning. Imagine that the model holds a picture of the dog in its left hand and the text a photo of a dog in its right hand. We calculate the dot product of these vectors. If they are pointing in different directions, we calculate the error and we force the manual to mathematically rotate the vectors until the image and the text line up perfectly. Simultaneously, we push away incorrect matches, pushing the dog's image away from the cat image. In this 3D visualization, you are seeing the result of the training. The vector for the word dog and the visual patch of a retriever and the audio spectrogram of a bark, they have all been pulled by billions of gradient descent steps into the same semantic cluster. This shared geometry is the physics of the meaning. This enables emergent cross-model reasoning. If I show the model an image of melting ice cream, it maps the concept of liquid and dripping. Because these concepts are geometrically close to the sound of splashing in the audio domain, the model can generate sound effect for an image it has never heard before. It isn't memorizing, it's traversing the map and magic, we have done it, right? But there's a price to this magic, and that price is calculated in quadratic complexity. The transformer's attention mechanism compares for every token to every other token. N tokens result in n square token interactions. For text with 1000 tokens, this cost is manageable. But images are dense, and video is catastrophic. A minute of video generates hundreds of thousands of tokens. When you square 100,000 tokens, you won't get billion operations. You get 10 billion operations per layer. The curve gets vertical, and that's a wall. So this issue is called as the token flood. A generic prompt is very tiny, maybe 10 to 20 tokens. An image breaks down into roughly 200 to 500 tokens, but video is a relentless stream of images 30 times a second. Transitioning from a text-only chatbot to multi-modal agent increases the data throughput by 10,000 times. Standard hardware is not designed for this avalanche. We needed to look deeper past the software down to the silicon itself. To really solve this, we cannot stay in the abstract world of Python code and neural weights. We have to go deeper. By deeper, I mean way deeper. To the metal. We need to understand the physical battlefield where this calculation happened. We need to look inside the GPU. Let's get in and open up the GPU. Now what you are looking at is the anatomy of the modern AI accelerator, like the NVIDIA H100 GPUs or the Grace Blackwell GPUs. There are two main characters in this story. In the center, the compute die. This is the brain. It connects the logic cores that perform the matrix multiplication. It is incredibly fast. Surrounding it are the stacks of HBM, high bandwidth memory. This is the storage warehouse. It holds gigabytes of video frame and the model weights. Connecting them is a microscopic highway of gold and copper traces. And this highway is where the performance goes to die. We call this the memory wall. The physical distance between the memory, HBM, and the compute die is only a few millimeters, maybe 10 millimeters. But to an electron moving at clock speeds of gigahertz, that distance is an eternity. In standard AI workloads, the powerful compute core spends up to 90% of the time idle, simply waiting for the data to travel from HBM to these cores via the wires. The bottleneck isn't how fast we can think, it's how fast we can fetch the memory. Now let's look at the standard attention and what problems it had and why is it more inefficient. So to calculate the attention, the GPU has to read the huge query and the key matrices from the HBM, which is a slow operation, compute the result, which is very fast, write that massive result back to HBM because it's too big to hold. It's a slow operation again. Read it again for the softmax step, slow operation. Write it back again, slow operation. Read it again for the final multiplication, slow operation. We are doing 7 round trips to the memory for one calculation. We are saturating the bandwidth with intermediate data that we don't even need to keep. Now this looks impossible to solve, right? But like your CPU which has a small cache, your GPU also has a small cache. There's a loophole. Inside the compute die, there's a tiny sliver of memory called SRAM, static RAM. The static RAM is like the cache in your CPU, is the working memory. It is blazing fast, orders of magnitudes faster than the HBM, but it's very tiny, maybe 20 to 40 megabytes per chip, compared to the 80 GB in HBM. The key inside is that if we can figure out a way to keep the data inside the SRAM and never write it back to the HBM in between till we finish, we can break the memory wall. Enter flash attention, introduced by Tree Dow and the colleagues at Stanford. It is an IO-aware algorithm. This is where the brainstorming is. It doesn't change the math, it gives the exact same standard attention answer, but it radically restructures the logistics. Now this is where it's absolutely mind-blowing, because we had algorithm that could predict the closest answer, but that results in loss of accuracy. By getting the same answer as standard attention, we are ensuring perfect accuracy but with all the improvements. We'll see how the improvements are done. It relies on three pillars: tiling, breaking the ocean of data into puddles; recomputation, trading math for memory; and kernel fusion, merging multiple operations into one. Now let's look into this concept by concept. Concept 1. Tiling. Now the attention matrix for a video is massive, too big to fit in SRAM, right? The standard attention tries to compute the whole thing, fails to fit it and spills it over to the slow HBM. Flash attention breaks this matrix into smaller blocks called tiles. It loads one tile into SRAM, keeps it there, performs all the necessary math, matrix multiplication, scaling, masking, softmax entirely within the fast cache and never writes to the intermediate. The giant matrix is never returned to the HBM. Now this tile is completely performed inside the SRAM, making it super fast and stores this answer only once it's done. Visualizing the flow, the difference is stark. In standard attention, we saw constant traffic back and forth, back and forth. In flash attention, we load this tile from HBM to SRAM once, we fuse the operations and compute the intents on the chip, then we write back the final result once. We cut the memory traffic by a factor of 8 to 10. By simply moving data less, the chip effectively becomes faster. Hey, what am I looking at? Recomputation? Does recomputation really save time? Am I gone crazy? Is the script wrong? What is wrong with it? Wait, to save memory during training, flash attention actually discards some intermediate results. It actually needs the emulator for the backward pass. It actually then calculates the entire thing again from scratch. Why? Because modern GPUs have become so fast at math, it is calculated in flops. You have these teraflops, something like that. Now, relative to how slow that the memory is, with using the bandwidth, like some gigabytes per second, that doing math is twice as fast than waiting for the data to come from the memory. Have you ever thought about this? That the calculation being so fast that you don't want to store the result and retrieve it back, but you want to do it from scratch every time, and this is more efficient. So something that we can just not get it the first time, but that is what it is. Because at technology, we have gone to such an extent that our computation is at another universe. But the bandwidth speeds are still in this universe. Therefore, now we are spending cheap compute to save bandwidth. That's what we are doing right now. Real master strokes. And finally, kernel fusion. In standard Python script, every operation load, add bias, activate, save is a separate function call that launches separate kernel on the GPU. Each one reads and writes to the memory, and you know what it is. Flash attention writes a custom CUDA kernel that fuses these vertically. It loads the data as the bias, applies the activation and scales the result all in one smooth motion, without ever releasing data back to the slow memory bus. Now you may ask, why are we doing all of this together? What does it result in? Is it a big change? Well, this is not even a marginal change that you are looking at. It's a paradigm shift. Flash attention typically yields about 3 to 5 times wall clock speed up compared to standard attention. But more importantly, we got a side effect boost up because of this. Because the memory scaling is linear rather than quadratic, regarding the sequence length, it unlocked the ability to process long sequences. We didn't just get faster models, we got longer models that could take longer context windows. This came as a side effect. What a bonus boost, man. I'd love to have that. This optimization is the engine behind the headlines that you see today. When you see the model with 1 million token context window, capable of reading entire novels, analyzing hour-long code bases, that is flash attention at work. When you instantly talk to a model in real-time video mode like Gemini Live and it responds instantly, that there is reduced latency of kernel fusion. And crucially, by reducing memory access, we cut the energy consumption by nearly 70%, making sustainable AI deployment feasible. It's just an all-in-one that you could just never believe that you got. But yeah, with every single innovation, there is a trade-off. A small trade-off though. The flash attention is incredibly difficult to implement. It requires writing raw CUDA C++ code, manually managing memory pointers and thread blocks. It is also hardware specific. The code is optimized for NVIDIA H100, might not run effectively on AMD chip or Google's TPU without significant rewriting. And due to this parallel nature of floating point addition, the result can be non-deterministic, meaning small numerical variations can occur. Basically, it is NVIDIA alone now. It's CUDA alone. And even in CUDA, it is only from some kind of version up. It doesn't work on standard T4, which is available to most of the people. It only works on some particular high-end GPUs, not in everything. So, and also the availability on AMD and Google's TPUs. Though TPU has something called XLA, that's a different story. But see, because of this is very limited in nature and very costly due to the availability of GPUs and the range of GPUs being very costly. So it's not accessible to all, but when it's accessible, it is the best. So looking back at the journey, we started with the dream of multimodal AI, unifying text, image and sound. This dream created a token explosion that our infrastructure couldn't handle and is not ready for. We hit the memory bottleneck. When our processors stopped for data, the memory was slowing, chugging down the street. But through the insight of flash attention, we optimized the hierarchy of silicon memory. We broke through the wall. The research papers detailing the architecture and flash attention algorithm are linked in the description below. They are the masterpieces of systems engineering and well worth the read. So the lesson here is simple. In the age of massive data, we cannot just throw more compute and call it a day. We have to be smarter about how we move data. The bottleneck of intelligence isn't always how fast you can calculate things. It is about how efficiently you can remember the data that you store. Also optimize every single thing.